Nikola Tesla once said, "If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration." Let's discover some secrets of the universe, shall we? Hey there, everybody. Welcome to episode number 478 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by yours truly, Amelia Dalton. Are you ready for a deep dive into the world of photonics? I certainly hope so. University of Chicago Assistant Professor Alex High joins me this week to chat about a new ultra-compact integrated photonic device that will lead us to new optical technologies. We're digging into the details of how Alex and his team at the University of Chicago's Pritzker School of Molecular Engineering have discovered a new way to guide light in one direction on a very tiny scale. We also take a closer look at a new element developed by this team and why it could lead to even smaller photonic circuits. So, without further ado, let's bring in Alex High. Hi, Alex. Thank you so much for joining me.
Hi. Thank you for having me on your show today.
Absolutely. Okay, so we're talking about a new ultra-compact integrated photonic device today that can lead to new optical technologies. So first off, Alex, can you give my audience a refresher on the differences between electronic circuits and photonics integrated circuits?
Yes, absolutely. I'm happy to talk about that because it's actually incredibly interesting. There's profound differences between how you can control electrons, which flow around in an electronic integrated circuit, versus how you can control light in an integrated circuit. In an electronic integrated circuit, essentially the way you control electrons is by applying electric fields. So electrons will follow electric fields. That's how you can get them to move around. So if you create a voltage difference across a transistor, you'll cause electrons to flow across the transistor. And then if you want to stop the electrons, you can, for instance, put a wall up by creating an electrostatic potential that blocks the flow of electrons. So this is very similar to how, for instance, water would flow down a hill. It wants to go from a high potential energy to a low potential energy. And this is how you can control these flows. On the other hand, with a photonic integrated circuit, the goal is to control the flow of light on a chip. And light is very different from an electron. So light essentially behaves as a wave. And as a result, the tools to control light are very different than how you would, for instance, control an electron. So for instance, unlike an electron, where you can change its energy by changing an electric field, for instance, it's actually incredibly difficult to dynamically control the energy of a photon. Typically, the energy of a photon is essentially directly locked to its frequency, and it's difficult to dynamically tune this. So you can't do the same thing where, for instance, you just create a hill and light will flow down it. It doesn't quite work like that. Additionally, light moves at the speed of light, of course, which is, very, very fast, the fastest thing in the universe. And it's also incredibly difficult to hold on to a photon for an extended period of time before it gets absorbed and disappears. So again, this is very different from electrons, which will always be there. A photon is like an excitation that's created, propagates, and then is absorbed, and then it disappears in this process. So how do we then control photons on chip, for instance, in an integrated fashion? So over the past couple decades, a variety of different tools have emerged to realize this. So to begin with, instead of using things like nanoscale electrodes and potentials to create channels like you would for electrons, we use what are called optical waveguides. So a waveguide essentially relies on using a high refractive index material to confine light in two dimensions to essentially create a channel for light. If you think about what happens when you have a low index medium like air and a higher index medium like water, you get reflection at the air-water interface. And at certain angles, you actually get total internal reflection. So if you're underneath a swimming pool, there's certain angles where if the angles are low enough, you can't see out of the pool. And this is total internal reflection. So how does this connect to photonic integrated circuits? Well, we can create these waveguides which basically rely on this principle of reflection at interfaces to fully confine and guide light. And typically you can actually guide light even at length scales comparable to the wavelength of light. So for visible light, which is 800 nanometers, we can sort of control how it propagates using these waveguides that are, a couple hundred by a couple hundred nanometers across. So this is how we guide light. But of course, what I've discussed so far isn't anything like an active process. This is like a passive process. And if we're talking about actual circuits, then we want to, realize ways to actively control how this light is flowing. So as I mentioned, you can't do something like dynamically control the energy. So you can't just create like a hill that the, photon can't go through. So instead, to actively control light, you rely on the properties of the wave nature of the light. And so you can use things like interference, where if you want to create a switch, you can tune the refractive index and basically create interference between two channels of light. So waves can add or subtract from each other, depending on whether they're in sync with each other. And so you can tune the phase of light, and you can use that as a way to control how it interferes with light. So that's one way you can control the propagation of light. You can also manipulate the degree of polarization of light. So as a wave, it's an oscillating electromagnetic field that has a polarization associated with it. And if you can manipulate that polarization, you can also manipulate how light propagates. And so to do this, you need materials that have nonlinear or tunable interactions with light. So for instance, materials where if you heat it up, the refractive index changes, which in turn changes the phase of the light. Or if you apply an electric field, the refractive index changes. So if you want to do something more complex, like we discussed how simple it is to like change the energy of an electron. If you want to change the energy of a photon, you actually have to use more complex nonlinear materials where you actually mix the light at different frequencies to generate different colors of light. So these are kind of the basic ideas of photonic integrated circuits and sort of how they compare and contrast with electronic circuits. So you might ask the question, why are they interesting? What are the applications of these things? Electronic circuits, anytime you're moving electrons around a material, you're going to get ohmic losses. So every metal has a resistance associated with it. And as a result, you always get heating and loss when you move electrons around. And this can make it very difficult to efficiently move information over long distances because of these ohmic losses and this sort of dissipation. Alternatively, photons can propagate for kilometers in fiber optics, in optical fibers, without losing any energy, or there's sort of attenuation is in the tens of kilometers scale. In direct contrast is sort of the nanometer or micron scales where you get dissipation in electronic systems. Additionally, you can use light to carry information coherently over extremely long distances. This is how optical communication works. Once you encode something in the phase or polarization of the light, it can propagate for very large distances without losing that information. And this is really critical to communication technologies. So then maybe the last part of this, since we're talking about photonic integrated circuits, is, okay, why do you want to do this on chip? And the essential idea there is that if you can do this on chip, you can essentially shrink optical components from the millimeter and centimeter scale to the micron length scale. So you can dramatically improve the scalability of your photonic chip, and you can reduce your power consumption as well when you can miniaturize these devices.
That makes sense. So, Alex, you and your team at the University of Chicago's Pritzker School of Molecular Engineering have developed a new way to guide light in one direction on a tiny scale. So, can you give me some details about this research and why it could lead to even smaller photonic circuits?
Yeah, absolutely. So I would say really the basic goal that we are working towards in this research is to create an ultra compact diode for light. So a diode meaning that it will only permit light to flow in one direction. So these are critical components in electronics. So an electronic diode, it doesn't matter how you bias it, it will only allow current to flow in one direction. These underlie all sorts of critical electronic technologies. And similarly, in the optical realm, isolators are incredibly important for things like laser sources that are sensitive to light that's reflected back into them. You have to have a way to stop that light because basically it can destabilize the laser. For things like, you might have heard of LiDAR, which is basically the use of optical fields to map out local areas. So LiDAR is, hopefully going to underlie self-driving cars, things like that, where basically you're using laser fields to monitor your surroundings, pulses of light to essentially map what's going on around your vehicle. These sort of things rely on isolators to prevent this back reflected light from coming in and destabilizing their sources and messing up their measurements. So this is, the basic idea of an optical diode, and they're incredibly important from a technological perspective. Diodes are super easy to see in nature. If you want to think about, lemmings going off a cliff, it's a one-directional process, right? And similarly, you can do this electronically by engineering your band structure of your material to create walls for electrons. But as I mentioned before, manipulating the energy of photons is actually very non-trivial. And instead of using that to control the flow of light, we look at other processes. To realize a diode for photons, what you need is something that people commonly refer to as non-reciprocity. And what non-reciprocity means is that light flowing in one direction experiences a different interaction with material than light flowing in the other direction. Light propagating one way sees something different than light propagating in the other direction. For instance, a different refractive index. And as a result, you can use this to permit flow of light in one direction and prevent it from flowing in the opposite direction. And typically, this is realized with so-called magneto-optical materials. So there's certain materials where if you apply a huge magnetic field, you can generate a small change in the refractive properties of the material that depend on the direction that light is flowing in the material. So these are these so-called magneto-optical materials. But these effects are typically very weak. And what you need to actually realize an isolator is something that is a couple inches in length scale with a huge magnetic field associated with it. So something that is, incredibly large from the perspective of integrated electronics or photonics. So these really large devices. So what we're working towards in our lab and what our research is sort of going towards in this project that we're discussing today is actually, realizing optical isolation and other non-reciprocal effects on chip at incredibly small length scales. So at micron length scales instead of centimeter or inch length scales. One way you can achieve this on chip, one way you can actually work towards generating these kind of interesting non-reciprocal effects is to actually leverage some of the interesting properties of optical fields when they're confined in these nanoscale channels. So basically, if you remember, we're confining light in these waveguides that are just a couple hundred nanometers across. And it turns out that basically to confine the light in this region, to sort of squeeze it into this 200 nanometer region, you actually generate some interesting properties in the polarization of the optical field itself. You actually get these optical fields that are rotating. Think about like wheels on a bike, like the spokes on a bike, they rotate, and that rotation is coupled to the direction that the bike is going. So if the bike is rolling in one direction, your wheel is rolling obviously in that direction. And then if you go in the other direction, the direction of this rotation flips. And something very similar happens to these optical fields of these nanoscale waveguides, where depending on the direction they're propagating, their polarization has a different rotation to it. So in this work that we're discussing today, we actually leverage this to generate these photonic circuits where light only couples into the waveguide in one direction. So we leverage this to actually break this condition of non-reciprocity. And the way we do that is, so the first step is having these optical fields in the waveguide. And the second step is to combine this with 2D materials that have polarization dependent interactions with light. And so the way we get these two to interact, these two-dimensional materials that have this interesting interaction with light and the waveguide, is basically we take a 2D material, in this case, a transition metal dichalcogenide, which is a semiconductor, and we print these waveguides directly on top of the 2D material. So we use a combination of electron beam lithography and other fabrication steps basically to define these nanoscale optical waveguides directly on this material. And then the optical fields of the waveguide will interact with the 2D material as light flows along the waveguide, it'll interact, since they're in the same place, the optical field of the waveguide interacts with the 2D material. Then what happens if, for instance, we create an excitation in the 2D material, like if we shine light on the 2D material, that light will couple into the waveguide. Basically, you can think of like the 2D material as like a beam splitter where, we come in with light and then this beam splitter couples light into our waveguide. And the way it couples in depends on the polarization of the input field. So if we come in with one circular polarization, then it only couples in one direction with the waveguide. The interesting thing about this 2D material is that all of these properties are electronically tunable. So we can dynamically switch it between coupling in both directions. So we come in and it goes right and left. Then when we apply an electric field to the material, it changes how it responds to circularly polarized light. And then it only allows light to couple in one direction. And we're doing this all as opposed to these centimeter scale devices that typically are used to realize these kinds of effects. We're realizing this in this, micron scale interface of this photonics and 2D material.
So, Alex, tell me a bit about the new element that you and your team developed in conjunction with this research.
Absolutely. So I would say the critical advance that we did was to essentially develop a way to integrate these photonics with this. Basically, when I talk about a 2D material, these transition metal dichalcogenides, they're literally a few atomic layers thick. They're less than a nanometer thick. And as a result, while they have some incredibly interesting optical properties, for instance, they interact so strongly with light that even this single monolayer material can reflect, like basically act as a mirror at certain resonances, like perfectly reflect light, but they're very delicate. It's a single atomic layer. And so I would say a critical advance that we did was essentially develop a method to print these photonics, to couple photonics to this delicate material system in such a way that it preserved the important properties of the 2D material that allow us to get this chiral tunable interface. That would be a critical technological advance, I would say. By doing so, we've maintained our ability to kind of electronically control the optical response of the 2D material and then dynamically tune between this regime where we get balanced coupling in both directions and unidirectional coupling.
So, Alex, you touched upon this a little bit earlier, but what kind of applications do you see these photonic circuits being used in?
One of the main goals of this research is to build essentially diodes for light and do it in an ultra compact fashion. Now, we haven't shown that at this point. What we've shown at this point is that we have this interface, this chiral interface between the waveguide and the 2D material. And now that we have that, there are ways that we can actually break the symmetry in the 2D material response to polarized light, which is something referred to as circular dichroism. We can engineer the 2D material such that it actually responds differently to one polarization of light versus the other. And once we have that, then we can put our interface together with that capability to actually generate these micron scale optical isolators. There are a variety of interesting technologies that can emerge from this. So I mentioned LiDAR. So self-driving cars, they want to have, 20 different LiDAR devices at different points to, basically map out in real time the surroundings of the car. And if you want to develop this efficiently and not have, these giant magnets involved in each device, then you need to figure out how to develop this at a more compact length scale. And so we certainly see this as progress towards that. So more ultra compact LiDAR devices. From a communications perspective, these isolators are also essential to multiplexing information. You want to prevent backscattering or information crosstalk when you combine information in a single channel. So isolators are a critical part of that. We see it as having applications in communications. And then in applications, even things like quantum networking, where we're trying to control how quantum information flows between different quantum nodes. So as ways to, study distributed entanglement or have entanglement protected communication, you need components like isolators to do this effectively. We sort of see our devices as having some impact in those areas of technology.
Absolutely. I can definitely see that, Alex. Now, it's time for your off-the-cuff question. Are you ready?
Sure. Yeah.
Because of a variety of reasons, a lot of us can't have our favorite foods these days. So, Alex, if you could have one meal right now, it doesn't matter if you need a passport to get there, it's on the other side of your state, the other side of our country, what would you have?
So probably my favorite, most addictive meal is, fresh pasta in Italy. So, I went there with my wife on our honeymoon, and I was basically eating 2 or 3, plates of pasta every meal, to the point where, it caused physiological changes in my body. I'm pretty sure I got swollen feet based on that, because, the pasta there is just so amazing. The tomatoes are so fresh. Everything's so sweet. The cheese is so perfectly aged. It all comes together perfectly. In particular, pasta alla matriciana in Rome. If I could go anywhere and get anything, I think that would be it. So go to Italy and eat ridiculous amounts of pasta.
That is a great answer. And now I'm definitely ready for lunch. Well, Alex, this was super cool. Thank you so much for joining me today.
Yeah, thank you, Amelia. It's been a pleasure talking with you about this.
Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EE Journal. If you're into Twitter, you can monitor our tweets at EE Journal TFM. And don't forget, if you would like to follow my personal Twitter account, check out Amelia D 1978. And hey, if LinkedIn is more your thing, sure, I dig it. You can follow us or me on LinkedIn as well. And we have a YouTube channel, youtube.com/EE Journal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series hosted by me. And you can subscribe to our EE Journal YouTube channel as well. Also, by clicking the links below the player on this week's Fish Fryin' page, you can subscribe to this here podcast through Spotify, Podbean, or Apple Podcasts. And remember, if you'd like to further support this podcast, please leave me a review on Apple Podcasts. It really does help. Also, if you'd like any further information about the stories covered in today's show, just head on over to eejournal.com and look for this week's Fish Fryin' page. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's AMELIA, at eejournal.com, or post a comment on our forums on EE Journal. For the week of April 22nd, 2022, I'm Amelia Dalton, and you've been fried.